Let us understand hydrolysis of different types of salts. We have mainly 4 different types of salts. Number 1, salt of strong acid and strong base. For example, NaCl, which is made from NaOH and HCl. Salt of weak acid and strong base, such as acetic acid and NaOH to give sodium acetate. Salt of strong acid and weak base, such as ammonium chloride. And the fourth one is salt of weak acid and weak base, such as ammonium acetate. So we will be studying the hydrolysis of all 4 types of salts and how it affects the pH of the solution. Now we know that the salts which are made up of strong acid and strong base should be neutral, so their pH must be equal to 7. And the second category, that is the salt of weak acid and strong base, should have pH greater than 7. That means they will give us some alkaline solution. The third category of salt is the salt of strong acid and weak base. So because you have the dominating acidic properties, so its pH would be less than 7. And the salt of weak acid and weak base can either have pH equal to 7, greater than 7, or less than 7. That depends on the relative strength of the acid and base used in the formation of this salt. If the strength of acid is more than the base, then this will be slightly acidic. If the strength of base used is more than the strength of the acid, then this salt will be slightly basic. And if both of them have the same strength, the pH can be equal to 7. Okay, we will take a representative examples of all these salts. For example, for the salt of strong acid and strong base, we will take the example of NaCl. We know that all these salts are strong electrolytes, so when dissolved in water, they will be dissociated into constituent ions 100%. There will be no equilibrium. This will be completely dissociated into ions. So NaCl will dissociate into Na plus and Cl minus ions. The example of a salt of weak acid and strong base, such as sodium acetate, this when dissolved in water will give us sodium ions and acetate ions. Example of the salt of strong acid and weak base that we will be discussing here is ammonium chloride, and this will also give us ammonium and chloride ions when dissolved in water. The third category is the salt of weak acid and weak base, that is ammonium acetate, and this will give us ammonium and acetate ions in water. Now, what happens when these salts are dissolved in water? Okay, like here, we dissolve NaCl and we get Na plus and Cl minus ions. So how this solution, we ensure that this is absolutely neutral and not having any acidic or basic properties. For this, we will study the hydrolysis of the constituent ions, whether these sodium and chloride ions further undergo hydrolysis. If yes, then this is going to change the pH of the solution. However, if we consider the hydrolysis of sodium ions, we see that when sodium ions are hydrolyzed, this should give rise to NaOH. But we know that NaOH is a strong base, and this strong base will not remain undissociated in water. This will be completely dissociated to give sodium ions and hydroxide ions. So that means the sodium ions on reaction with water do not give you any undissociated base, rather it will again split into sodium ions. And the H plus ions given here would combine with OH minus ions to give you water back. That means this reaction cannot go in the forward direction. Now let us see if we try to hydrolyze chloride ions. Chloride ions, when hydrolyzed with water, will give us HCl and OH minus ions. So in this case, the HCl is a strong acid. Again, this will not remain undissociated in aqueous medium, and it will dissociate into H plus and Cl minus ions. That means hydrolysis of Cl minus ions will give you back, the Cl minus ions, yes. So Cl minus ions will be obtained again. That means these ions have not undergone any kind of reaction with water. So we say that the salt of strong acid and strong base, both the constituent ions, do not undergo hydrolysis. Because of this, there are no H plus or OH minus ions produced in the water, and the pH remains equal to 7. Now we will take another case, the salt of weak acid and strong base. So here we have an example of sodium acetate. Sodium acetate, when dissolved in water, will give you the constituent ions, sodium ions and acetate ions. Now let us see the hydrolysis of these ions. As we have discussed, that sodium ions will not undergo hydrolysis because of the formation of strong base, which will further split to give back the sodium ions. Now what happens when acetate ions undergo hydrolysis? Acetate ions, when combined with water, they will produce certain amount of undissociated acetic acid. And we know that acetic acid is a weak acid. So this weak acid will not undergo 100% dissociation to give back the acetate ions. There will always be an equilibrium between acetate ions and the undissociated acetic acid. So in this case, we will say that certain amount of hydroxide ions will be produced as a result of hydrolysis of acetate ions. So because of these hydroxide ions, we say that solution has become alkaline. So the pH of such salts are alkaline, or we can say this is greater than 7. And why this is alkaline? This is because of the hydrolysis of the constituent anion. Cation is not undergoing hydrolysis, only the anion is undergoing hydrolysis, producing OH minus ions. In a similar way, okay, so we first discussed the calculation of pH and hydrolysis constant and the degree of hydrolysis of this type of salt, that is salt made up of weak acid and strong base. Okay, now we know that hydrolysis of anions are only going to happen in this case. Cation will not undergo hydrolysis. So if we consider the hydrolysis of acetate ions, so we know that at equilibrium, the concentration of acetate ion would depend on the degree of hydrolysis. That is, its concentration would be C into 1 minus alpha H, where alpha H is the degree of hydrolysis. And the amount of undissociated acetic acid produced will be equal to C alpha, and the same amount of OH minus ions will be produced. How can we calculate this hydrolysis constant? This is the equilibrium constant of this reaction. Considering water to be practically constant, the concentration of water remains the constant. So KH can be written as the product of concentration of the products here divided by the concentration of reactants. So we have undissociated acetic acid and OH minus in the numerator and acetate ions in the denominator. Replacing these with their amounts, we can write it is equal to C alpha into C alpha upon C into 1 minus alpha. And we can assume here that alpha, that means the degree of hydrolysis of these acetate ions, is quite small. So we can say the degree of hydrolysis is very, very less as compared to unity. And for an approximation, we can take that 1 minus alpha is approximately equal to 1. With this approximation, our equation reduces to KH equal to C alpha square. Because 1 minus alpha, we can consider this is equal to 1. So C will cancel out C and we get KH is equals to C alpha square. And from this, we get our equation of degree of hydrolysis. That is, the alpha H is equal to under root of KH upon KC. That means if we know the hydrolysis constant for a given hydrolysis of the anion, we can calculate the degree of hydrolysis. And also if we know the concentration. However, in case the KH is not known, generally in literature, we are given the values of acid dissociation constant and not the hydrolysis constant. So how can we obtain hydrolysis constant if the acid dissociation constants are given to us? So let us see how do we calculate KH first. Now from this expression, we have got the KH as the product of the concentration of the products upon the concentration of the reactants. So here, if we divide both the numerator and denominator by H plus ions, we see that we have got an expression of ionic product of water as well as the ionization constant of acetic acid. Now see that the product of OH minus into H3O plus can be written as Kw. And if you see this expression, the numerator is undissociated acetic acid divided by acetate ions into H plus ions. This is nothing but the inverse of Ka. Okay, so this reaction is the opposite of ionization of acetic acid. So if we just reverse it, this becomes Ka. That means the Ka will be equal to acetate ions into H plus ions divided by undissociated acetic acid. So this is nothing but inverse of Ka. So we can write Kh is equals to Kw upon Ka. So you see that we have multiplied both the numerator and denominator by H3O plus, and we have obtained this expression. So from literature, we know that the value of Kw is 10 raised to the power minus 14, and the value of Ka for acetic acid, we know that it is 1.8 into 10 raised to the power minus 5. So we can easily calculate the value of Kh for acetate ions. And once Kh is known, we can calculate our degree of hydrolysis. Now, once we know Kh as well as alpha H, we need to calculate the pH of the solution. We know that the solution will be alkaline due to the production of OH minus ions. So to know or to calculate the exact pH of the solution, depending on the concentration of salt, we can start calculating from the expression that these concentration of OH minus ions is nothing but it is equal to C into degree of hydrolysis. So the initial concentration is known, and if alpha H is known, you can directly calculate the concentration of OH minus ions. And if the expression for OH minus ions are known, you can calculate the H plus ions from the equation that H plus ions are equal to Kw upon OH minus ions. So you can obtain your pH value from this expression. So finding a proper equation, a representative equation for calculation of the pH, we can replace this alpha value by Kw upon C. So we have just derived that the concentration of OH minus is C alpha. So the concentration of H plus would be Kw upon C alpha. So C alpha can be written as C into inverse of C upon Kh. And we have just derived that Kh is nothing but it is equal to Kw upon Ka. So putting the value of Kh here, we finally get the representation of H plus ions in terms of Ka and Kw by this equation. And if you want to convert this H plus ions into the pH equation, you just have to take negative logarithm on both the sides, and we simplify this equation to obtain our final equation as pH, which is nothing but minus log of H plus into half, and minus log of Kw will be written as pKw, minus log of Ka can be written as pKa, and minus log of minus 1 over C can be written as plus log C. So this is an expression for calculating the pH directly from the values of pKw, pKa, and log C without going into any calculation of the degree of hydrolysis or hydrolysis constant. So we know that pKw is equal to 14, pKa for acetic acid is 4.75. So you just have to use the value of the concentration of the salt to obtain the expression for pH. So this is a straight method to calculate pH once you know the pKa and log C. Okay. So moving on to the next type of salt, the salt of strong acid and weak base, for example, ammonium chloride. So here, when the salt is dissolved in water, it is completely dissociated into ammonium ions and chloride ions. these ammonium ions, when dissolved in water, will be again in equilibrium with the undissociated ammonium hydroxide, and an equivalent amount of H plus ions will be produced. Now, this being a weak base will not be 100% giving you back these ions, but there will be only certain concentration of ammonium ions and certain concentration of ammonium hydroxide ions in the solution. So there will be an equilibrium, and we will have H plus ions equal to the amount of ammonium hydroxide undissociated form. The other ion which is produced, that is Cl minus ions, will not undergo hydrolysis as this produces a strong acid. So we say that only the constituent cation will undergo hydrolysis in such type of salt, giving rise to H plus ions in the solution, and hence the pH of such types of salt will always be less than 7. Because we are producing more of H plus ions, this will be an acidic solution. So let us calculate the pH, hydrolysis constant, and the degree of hydrolysis for such salts. So we will consider only the hydrolysis of ammonium ions, that is the cation, and we write the equilibrium concentration of these ions here, and we also write the expression for hydrolysis constant by using our formula of the concentration of the products over the concentration of the reactants. And substituting the values of these concentrations, we get KH is equals to C alpha square upon 1 minus alpha. And by assuming that alpha is very, very small as compared to 1, we simplify our expression as KH is equals to C alpha square. Or we can say that degree of hydrolysis is equal to under root of hydrolysis constant over the initial concentration of the salt. So again, we can have the expression of KH in terms of KW and KB, because here we are considering the equilibrium of a weak base. So we will be deriving KH in terms of KB and KW. So we see that from this expression of KH, we can multiply the numerator and denominator by OH minus ions, and this we get KW, H plus into OH minus will be equal to KW, and this is an expression of the inverse of KB, that is the dissociation of ammonium hydroxide expression. This is 1 over KB, so we get KH equal to KW upon KB. So we can always calculate hydrolysis constant if we know the base dissociation constant, and of course KW is known to us at 25 degrees centigrade, which is equal to 10 raised to the power minus 14. Okay, for the expression of pH here, we again see that at equilibrium the concentration of H plus ions produced are equal to C alpha, and if we substitute the value of C alpha, we can get the expression for H3O plus ions as equal to under root of KH into C. Now substituting the value of KH as KW upon KB, we get the expression of H3O plus as under root of KW into C upon KB. To have an expression of pH, we have to take the negative logarithm on both the sides. So taking minus log on both the sides, we get pH, which will be equal to half into pKW minus pKb minus log C. So this is a straightforward expression for calculating the pH of a salt made from strong acid and weak base. Once we know the value of pKb and the concentration of the salt, we can straightforward calculate the pH of the salt. Now we move off to the fourth type of salt, that is the salt of weak acid and weak base, such as ammonium acetate. Now in this case, the dissolution of this salt in water will give rise to both ammonium ions and acetate ions, which are the ions of a weak acid and a weak base. So both of them will undergo hydrolysis. They will form an equilibrium with the undissociated acid and undissociated base. So in this case, we see that there are no H plus ions or OH minus ions that are produced. So the solution should remain neutral. But in this case, again, we have discussed that it depends on the strength of the acid and the base that is used to make the salt. If the strength of acid is more, this salt will have a acidic pH. If the strength of base is more, then the pH of the salt would be alkaline. Okay, so we will find out the expression for calculating the pH of such types of salts by using the same format. So here we have understood that both the cation as well as the anion of this salt will undergo hydrolysis. Okay, in this case that we are discussing, that is ammonium acetate, the acid dissociation constant as well as the base dissociation constant for both these constituents is actually the same. That is, pKa and pKb is absolutely the same for acetic acid and ammonium hydroxide. So in this case, we can say that pH will be equal to 7. So how do we find the expression for the hydrolysis, degree of hydrolysis in this case? Again, we will write the hydrolysis equation where ammonium ions are in equilibrium with undissociated ammonium hydroxide and the acetate ions are in equilibrium with undissociated acetic acid. So the expression for hydrolysis constant can be written as the concentration of products upon the concentration of reactants. Substituting their amounts, we get KH equal to alpha square upon 1 minus alpha square. So interestingly, you will see here that the hydrolysis constant does not depend on the initial concentration of the salt itself. It only depends on the degree of hydrolysis. So to find the expression for degree of hydrolysis, we rearrange this equation as alpha upon 1 minus alpha is equal to under root of KH. And on rearranging, we get alpha H is equals to under root of KH upon 1 plus under root of KH. So this is our expression to calculate the degree of hydrolysis. Now, to find the degree of, to find the hydrolysis constant in terms of Kw, Ka and Kb, we rewrite this expression of KH and then we multiply the numerator as well as the denominator. In this case, we will multiply it by both the H plus ions as well as the OH minus ions. So we do not have any H plus or OH minus ions in this expression. We multiply the numerator and denominator by both these ions and we get that this will be equal to Kw, that is the product of H3O plus and OH minus ions will be equal to Kw, and this set acetic acid and acetate ions and H plus ions, this will constitute our Ka, that is 1 over Ka, and this combination, that is ammonium hydroxide upon ammonium ions into hydroxide ions, this constitute 1 over Kb. So our final expression for the hydrolysis constant for such salts will be equal to Kw upon Ka and Kb. So here we see that we can calculate the hydrolysis constant from the acid dissociation constant and the base dissociation constant of these weak acid and weak base which form the salt. Now to calculate the pH of such salt, we have to take only one of the acid or the weak base or weak acid expression. So let us take the acid expression because we get H plus ions directly in this expression. We will consider the dissociation of acetic acid, and from that we can write the expression of Ka as equal to acetate ions over acetate ions into H plus ions over acetic acid undissociated. And from this we can have our expression of H plus ions, which is equal to Ka upon undissociated acid over acetate ions. Now we know that the amount of undissociated acetic acid, if we go back, we see that the amount of undissociated acetic acid was C alpha and the amount of completely acetate ions is equal to C into 1 minus alpha, and we substitute these values in that expression of H plus ions. So for acetic acid we can write K alpha, and for acetate ions we can write C into 1 minus alpha. So simplifying this, we get H plus ions is equal to Ka into under root KH, and we know that the expression for KH is equal to Kw upon Ka into Kb. So final expression of H3O plus ions will be equal to Kw upon Ka, sorry, Kw into Ka upon Kb whole under root. To find the expression for pH, we take negative log on both the sides, and we get the expressions for pH as pH equal to half pKw plus pKa minus pKb. Now in this expression, as compared to the earlier expression of different salts, we see that the pH does not depend on the initial concentration of the salt used. It only depends on pKa and pKb. In case pKa and pKb are equal, for example, in case of ammonium acetate, these both values are equal. So pH will be equal to half of pKw, that is 7. However, if pKa is greater than pKb, the pH would be less than 7. In case pKb is greater than pKa, sorry, if pKa is greater than pKb, then we get pH greater than 7. Yes. pKa greater means it is a weaker acid. And pKb, if it is greater, that means it is a weaker base, then we have pH less than 7. So this is our summary of the formulas that we have derived for the salt of weak acid and strong base, salt of strong acid and weak base, and salt of weak acid and weak base. So we need to remember these formulas for using, for doing our numerical problems. I have shown one sample problem for you here. So let us see how we do, how do we do this. The degree of hydrolysis of sodium acetate. Sodium acetate is the salt of strong base and weak acid. So degree of hydrolysis in its 0.01 molar solution is 0.023%. Calculate the hydrolysis constant and the concentration of OH minus ions. So they are asking us not to calculate the H plus ions or pH, they are asking us to calculate the concentration of OH minus ions. So first we will find out what is given. Given is the concentration of the salt, 0.01 molar. Given is the hydrolysis, degree of hydrolysis, that is 0.023%. And we have to calculate KH and the concentration of OH minus. So we can calculate alpha in terms of its unitless value by finding out the percentage, that is 0.023 divided by 100. So alpha is equal to 2.3 into 10 raised to the power minus 4. The concentration of the salt is given as 0.01 molar, and using this expression that KH is equals to C into alpha square. Here we have assumed that alpha is very, very small than 1, which is a correct assumption, because if you see in this case, alpha H has value of the power of minus 4, 10 to the power of minus 4, which is very well less than unity. So our assumption holds good here. So KH is equals to alpha H square. Putting the value of C and alpha, we get the value of KH to be equal to this 5.29 into 10 raised to the power minus 10. And from this expression of hydrolysis of acetate ions, we know that the concentration of OH minus will be also equal to C alpha, as these and these will have the same values of C alpha. From C alpha, we know that alpha, and we also know the value of C. We can calculate the concentration of OH minus ions here. Okay. So we can have different numerical problems for you in the assignment that I'll give you. Just go through them and try to solve.